Okay, so welcome back to the second part of the first lecture regarding the dynamical semigroups and their generators. Just a brief recap of what we did last time. So the whole of last lecture was essentially functional analysis, and in particular, we arrived at the concept of a dynamical semigroup. That's a set of maps that take operators from a Banach space to operators in a Banach space. They satisfy these three properties. Strong continuity, I remind you, is the fact that every Cauchy sequence terminates and the limit is in the space. And the dynamical part of the semigroup just means that if I give you positive operators and I apply the map, then I have to end up with positive operators, and that the map preserves the trace. Okay? And if you remember, the only reason why we did this was to introduce a very important theorem called the Hille-Yoshida theorem, which tells you that there exists an operator that generates the semigroup. Okay, and this operator I normally denote as lambda. Okay, so that's where we ended up last time. Actually, in the last lecture, I started proving the first theorem in this paper here. But I also realized that I was very tired and I said things that were incorrect and also wrote down things that were incorrect. So we're going to go through the theorem again. Okay, and this time I'm going to try and state it correctly. Okay, so let's start. Before I start, maybe the best thing to do would be just to give you what the plan is. So effectively what this paper does is it does the following. First, it proves necessary and sufficient conditions for any L to be a generator of a dynamical semigroup. Okay? The second thing is they give you necessary and sufficient conditions for any map, for any dynamical semigroup to be a completely positive dynamical semigroup. Okay? Then the third step is to use these ideas to impose the conditions that the generator needs to have in order that the semigroup is completely positive. And then they just derive exactly the form of this generator. Okay, so this is what we're going to do as well. We're going to follow exactly that logic. So with that said, let me start by stating the first theorem. Again, and I believe I'm using the same notation as in the paper by Gorini, Kossakowski, and Sudarshan. So I think it's called theorem 2.1 because it's in section 2, so I call it theorem 1. Okay? So we have a dynamical semigroup, which we are going to assume already the Hille-Yoshida theorem. Okay. Next, we're going to introduce a complete orthonormal set of projectors. Okay, since they are projectors, this means that we can write every operator like this, where these vectors form an orthonormal basis, okay? Then the L that appears here we say generates It generates a dynamical semigroup if and only if the following two conditions hold. The first one is called the trace conservation. That is, that this condition here is equal to 0. Remember that everything we're talking about here are finite dimensional Hilbert spaces. In other words, n-dimensional Hilbert spaces. So the Banach space is also finite dimensional. And the second condition is called infinitesimal positivity. Which implies that the trace okay? So these are the two things we need to prove. So it's an if and only if, so we need to prove both directions. So the first direction is we're going to assume that this is true, okay? So that this is a dynamical semigroup that using the Hilo-Yosida can be written like this, and that we have a set of projectors, and given that this is true, we're going to prove that these two things hold, okay? So, in particular, we're going to use the following property. So if it's a dynamical semigroup, then it has to satisfy these two conditions, right? And the other thing we're going to use is strong continuity, okay, of the dynamical semigroup. So to prove the trace conservation, we have that the trace sorry. First of all, let's do this by strong continuity. I can write this as, let me write it with this small circle notation. This essentially means E delta T composed with E delta T composed with E delta T, and this happens n times, and delta T is just T over n, okay? So I'm using this property for the fact that I'm strongly continuous, so I can divide, sorry, I'm using the second property here, right? If it's a dynamical semigroup, I can go to T by composing the maps, okay? So I'm choosing to compose n times a map that advances me by an amount T over n, okay? And then since all these maps are going to be form part of the group, the next thing I'm going to do is I'm going to use the Hilo-Yosida theorem and a Taylor expansion to prove the following property. The second property here, this trace conservation, follows from here. If it's a dynamical map, it means that this thing, okay, or rather, let me write it like this. 1, which is the trace of rho, should equal to the trace of V delta T of rho, right? And now what I'm going to do is I'm going to Taylor expand this E delta t from here. So I'm going to write this as the trace. We have here the identity plus delta t L plus something which will be of order delta t squared acting on rho. Okay? Now what I'm going to do is I'm going to choose rho to be some projector in here. Okay? And notice that what I'm going to do now is, if I multiply this by the identity, this is the same as this, sorry, the trace of the identity but now remember I have a complete orthonormal set of projectors, so I can write this as the trace sum over k pi k E delta t of rho. And by linearity, I can move this outside. Sorry, I know I should have done this before, but here, let me rewrite this. This will be the sum over k, the trace pk, and now I expand this to first order. This acting on rho. Now I put rho equal to pi L, so this will be the sum over k, the trace pk, identity here, so I will get pi L plus delta t, this generator acting on pi L, plus things that are of order delta t squared. Okay? And then you will recognize, using the properties of the trace, that what I have is the trace of pi k pi L plus delta t, the sum over k, the trace of pi k L pi L plus things that are of order delta t squared, right? This is 1 when L equals k, and otherwise it's 0. Right? So this is 1 plus delta t, the sum over k, right? But remember, this had to be a dynamical map, which means that this one here equals everything here, we had an equal sign, which means that this thing here must be equal to 0 for all k and L in 1 to n. Okay? Okay? To prove the second property, we have to show this second property implies we have to prove positivity here. So remember that to show that this implies that if I put here any phi, right? That's what positivity means. Okay? Now what I'm going to do is, again, I'm going to choose so that this essentially reads as follows: phi which you should recognize as the trace okay? This is a positive operator, so what I'm going to do now is also I'm going to choose this state from my completely orthonormal set of operators. In particular, I'm going to choose it to be pi k for some k different than L, okay? The idea here being that I'm choosing an orthonormal basis and I'm looking at the action of this map on the diagonal, and what I'm looking at is how much of the probability in this space is moving to the off diagonals, okay? So this is why I'm choosing a k different than L. So if you think of this as a matrix, right? This is an n by n matrix. So I have n squared entries here. I'm picking an entry here in the diagonal, and what I'm checking at here is what happens to things like this. How much are things moving away from the diagonal, okay? And if it's positive, it means that this thing this flux that's moving away from the diagonal has to be a positive thing. So essentially our second condition, this thing here reduces to the trace of pi k e delta t of pi L, right? And now what I do is, again, I do the Taylor expansion, that this thing is equal to the trace pi k, here I have identity plus delta t L plus something which is of order delta t squared acting on pi L. Okay, this is equal to the trace. Here I have pi k pi L plus delta t, the trace pi k L of pi L plus order of things that are smaller, that are small in delta t. Since I chose k different from L, this term here is 0. And since in order for this to be a dynamical semigroup, I need this to be bigger than 0, it follows that this guy has to be bigger than or equal to 0 for all k different from L. Okay? So that's the if part. Now let's do the only if part. Now let's show that if these two conditions are true, okay, that if these two conditions are true, then what we get is a dynamical semigroup, okay? Okay? So now let's do the only if part. Okay, for the only if part, we know that for any there exists an orthonormal set of projectors, P, P such that this rho can be written like that, right? It's by the spectral decomposition, correct? Yep. Okay, so let's now take the trace of L of rho. This is the same as doing this. Right? This is the same as doing this. Right? But now remember, we are assuming that these things are true, which means that this thing is 0, which means that this is equal to 0, which is what we want, because remember, we wanted it 0 here so that the trace of the dynamical map is equal to 1. Right? This is equal to 0 by 1. Right? And now for the second property is we're going to choose in other words I choose here lambda k for some k is 1 and the rest is 0, okay? And then what I'm going to do is I'm going to calculate the trace of this guy, okay? Remember, this is the same thing as what we did effectively here. I just choose now a phi, which is a pi k, and I choose my input as L. So this thing we knew from before. This thing can be written as, right. Something like that, right? This just from the computation we did here. Right? In fact, it's here. Now this, there are two possibilities. Either I choose pi k, either I choose k to be the same index as L, in which case this will be 1 plus delta t, the trace of pi L, L, pi L, plus things that are of order delta t squared. Or I choose k different from L, in which case this is just delta t. This is for k equals L, and this is pi k L, pi L, plus order delta t squared. This is for k different from L. But now remember, we're assuming that these two things hold. So here, this condition tells me that this is bigger than 0, okay? And then I also know from the first condition that the trace of this has to be 1, right? That the trace of pi L, which is less than 0. Okay, it also has to be in absolute value less than 1. So in order to preserve the trace, this has to be equal to all that. These we know are bigger than 0, so these guys are all bigger than 0. There's a negative, this is less than 0, so this is all positive, and we have a dynamical map. Okay? Okay? Good. The next thing we need is necessary and sufficient conditions for when a dynamical group is a completely positive dynamical group. Okay? So far here, I only demanded positivity. Remember, I only demanded that this is bigger than 0. Now I'm going to demand complete positivity, because if you remember, complete positivity is the concept that if my system is entangled with some other system and I do something to it here, the result has to be a positive operator. Okay? So in the paper, this is downgraded to a lemma. Okay, and it states CP means completely positive. And again, we have an if and only if. So in simple words, this is a completely positive dynamical semigroup if its extension is a semigroup. It's a dynamical semigroup. Okay? Yes.
So this is specifically for the extension acting on basically that same space square, or can you have
yes.
space have a different dimension?
So remember, okay, this is a very good question. So remember that we are dealing with finite dimensional Hilbert spaces. Okay? The definition I gave you of complete positivity is that for any dimension of the extended space, the operator is positive. But since this is finite dimensional, it suffices for us to check for a Hilbert space of the same dimension as the original one. Why? Because if you give me any n smaller than that, I can always append it with rows and columns to zeros and make it the same dimension, okay? So it suffices for us to check in the same dimension, okay? Okay, so here's the proof. First, we're going to assume that if this is a completely positive dynamical semigroup, that this is true, okay? So the if part. Right? Now, to prove the semigroup property of this one from this one, it's really easy, right? Okay? So, what does it need to be a semigroup? One, we need that this thing is the identity, tensor the identity, right? This is always the identity. This is a semigroup by definition, so if I put here 0, this is the identity. The second thing is that this also trivial, because identity remains the identity, and this is by definition a semigroup, so it definitely satisfies this, right? And the third property is strong continuity. Well, this is also very clearly follows because I do nothing to the second system, and if I pick, so if you remember, strong continuity was the limit that if I take t to t0, then this map on any state minus this map well, this is true because this, by definition of this being a semigroup, this is the only parameter that depends on t, is strongly continuous, so the extension is also strongly continuous, okay? Right? Also note that the converse is also true. So let me say it now so that it saves us time. If this is a dynamical semigroup, if this is a semigroup, then so is this one, right? Because all I need to do is simply trace out this system here, okay? So if this is a semigroup, then so is this one, okay? Very trivially. Good. So remember that we start with the if part. We're also assuming that this is completely positive, okay? But complete positivity right? So far we proved the semigroup property. Now I'm going to prove that it's a dynamical semigroup. So ET being completely positive implies that this thing right? Which makes the extension positive, right? It's also trace preserving because this one ET is a dynamical semigroup. The identity always preserves the trace. So this ET tensor I is a semigroup that is positive and trace preserving, so it's a dynamical semigroup. Okay? Do you want me to show you the trace preserving part, or are you okay? If you want, let's prove the trace preserving part, because Miriam is not happy. Okay? So far, right? Positivity, so this proved condition 2 for a dynamical thing, and let's prove condition 1, which is the trace preservation. This is not entirely obvious, but let me do it the different way. Okay, now I've written it like this. We can also, if you prefer, and I find this much better, we can write it like this. Remember that complete positivity, it doesn't matter which way I write the operators, okay? So the only reason why I'm going to show you why this is true here is because this is very easy to see. Imagine that we take two-dimensional systems, okay? So we take a 4x4 matrix. Here is your 4x4 matrix, okay? It's generally full of entries, right? This is what this A is. Imagine that this is two-dimensional and this is two-dimensional, okay? Split this matrix into 4 parts, okay? And let's call this in space A and this space B, okay? This basis here can be written as 0 Alice. So this part here is the 0 for the A part and the 0 for the A part. This block here is the 0 for the A part and the 1 for the A part. This part here is 1 for A and 0 for A, and this one is 1, 1 for A. Okay? And this entry here is the one where A is 0, 0 and B is 0, 0. And this entry here is the one where A is 0, 0 and B is 0, 1. And this entry here is the one where A is 0, 0 and B is 1, 0. And here 1, 1, and the same thing here. This is 0, 0 for B, 0, 1 for B, 1, 0 for B, 1, 1 for B, and the same here and the same here, okay? This is what this decomposition is effectively doing, okay? This is also the same thing. The only reason why I wrote it here is because it's very simple to see. This is A, and this is the B matrix, is this one here. For example, for 0, 0, this is the A 0, 0 matrix. This is the A 0, 1 matrix, okay? If you write it this way, then what do you fix? You fix the B entries. So here's 0, 0 for B, 0, 0 for B, 0, 0 for B, 0, 0 for B. And this will be the matrix on A. It will be have entries here, 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 and here. 0, 1 for B is this one, this one, this one, and this one. 1, 0 for B is this one, this one, this one, and this one. And 1, 1 for B is this one, this one, this one, this one. Okay? So it's just a way to express a general matrix in this basis, okay? Everybody can see that? You clear? This is very handy. It also works if I had more, right? If this matrix was bigger, then here will be the 2, and then 2 below, okay? It works for any dimension, okay? So I'm going to stick with this notation, okay, just to be consistent. Why am I writing it like this? Because remember, in order to be a dynamical semigroup, I have to show, we've shown that this is positive, now we have to show that it is trace preserving. Okay? So now if I do the trace, this should be the trace on A. What is the trace on A? Well, if I write A like this is equal to the sum over ij from 0 to n minus 1, the trace of aij times the trace of ij. Here I've used the property that okay? But the trace of ij is what? This is a delta ij, which means that this becomes the sum over I of trace of aii, which means it's the trace of this block and the trace of this block, and the trace of this block is a diagonal, and the trace of this block is a diagonal, which is what the trace is, right? So now let's do it for this side. This side here tells me that this is ET tensor identity. Now let's write A in this form, right? This becomes the trace, well, the sum, I pull the sum outside, this becomes the trace the identity on ij is just ij. Now I use the same property. This is the sum ij trace of ET aij times the trace of ij. This thing here is delta ij. So I have the sum over I, the trace right? But now remember, this is a dynamical map, which means that this is equal to the trace of aii, which is what this is. So the extension is also a dynamical map. Okay? All good? It's not difficult, it's just that you have to have your wits about you. Okay? You have to really work, okay? Now let's prove the converse. In other words, let's assume that this is a dynamical semigroup, and let's prove that this is a completely positive dynamical semigroup, okay? So we've already shown that this is a semigroup, right? Because from the argument we did here, if I trace out everything, then the reduction is a semigroup. We only have to prove now the dynamical part and the complete positivity part. So for the dynamical part, the proof is the same, right? At least for the trace preservation, right? To prove the dynamical part now, I have to prove that given that this preserves the trace and is positive, this preserves the trace and is positive. Okay? To show that it preserves the trace, the argument is the same. We go from here, right? I assume that this preserves the trace, and then I show that this is indeed the case. That for this to preserve the trace, this must equal this. Okay? In fact, here, for the sake of the people in YouTube, let's do it. So let's assume is equal to this. Remember that this, using this decomposition here, can be written as the sum over I from 0 to n minus 1, the trace of A, I. Okay? By assumption, right, this is equal to the trace of ET tensor I acting on sum over ij, aij tensor ij, which is equal to the sum over ij, the trace of ET on aij tensor ij, which is equal to the sum over I, trace of ET aii. So this is equal to this, which implies that okay? The hard thing to do is to show that since this is a dynamical semigroup, is to show that positivity of this implies that the reduction is also positive. Okay? For this, I have to use a theorem. Okay? Which I will prove in the next lecture. It is a very famous theorem. Okay? Let me be bold and say famous theorem, okay? It normally goes by Choi's theorem. Nowadays people call it the Choi-Jamiolkowski theorem, okay? And the theorem states I'm going to be very suggestive here. Rather no. Okay. So I'm going to consider a maximally entangled state. Well, up to normalization, a maximally entangled state, okay? I'm going to define this operator, which is essentially my map, my linear transformation acting on one part of this maximally entangled state. And then what Choi proved is that ECP, if and only if this operator is positive, okay? And with this I can actually prove that exactly what we want. Because by definition, remember, the assumption was that this is a dynamical semigroup, okay? Which means that this is trace preserving, which is we proved. And we also have to prove that it's positive. Positive means I choose this as an input state, right? And the resulting operator must be positive. But this is what Choi tells me. And this is true if and only if this guy is completely positive. Okay? And that's it. Okay? Good? Fantastic. So, now that we have everything we need, the rest of the proof is simply a structural proof, okay? How to obtain a form for this L. And to do that, I need to write down, we need to prove two lemmas. One of them is a little bit long-winded, okay? But I will skip one part of the proof a little bit, and I will assume another part. I don't think we will lose anything. Okay, so let's go here. This is the second lemma. Okay. Okay? So basically it tells you, give me any linear map from bounded operators on a Hilbert space to bounded operators on a Hilbert space. I define an orthonormal basis on the input space. Okay, notice that if the Hilbert space is n-dimensional, then the bounded operators have dimension n squared. So I need n squared elements in this basis. And with respect to this basis, the action of the map is given like this. Okay, to prove this action I have to, let me just say, okay, one naive way of doing this would be the following, right? Since this is a basis, I can express A in that basis, right? I can also express the output of this map in that basis, which means that you can put here a trace over GK A, GK, and out here another trace, GL, of this output. We use linearity, and you're going to get out something which is going to look a little bit like this, except it won't have GKA, GK dagger, okay? In fact, there is nothing wrong with you doing that. If you do that, what you have is an equivalent representation to this one, okay? And to show you why it's equivalent, I will do the following trick. We're going to use this trick a lot in the next lecture, so I might as well tell you now. In fact, you saw me do a faux pas of it here. Remember, I started writing identity here, and then I erased it. And the reason is this one. Okay? This is just a fancy way of doing the following. This is a matrix, right? So this matrix, A, if I asked you to write it, you would write it like this, no? Right? All this isomorphism is doing is telling you take this ket and turn it into, sorry, take this bra and turn it into a ket. In other words, and now you're making it a vector. Okay? So here, this omega, you should recognize it as, sometimes also people use this double ket notation. This is the identity written in vector form. Okay? Right? Do you see it? Good. So if I use this, then you should verify the following identity. One of them at least, there's more, but for now we're only going to need one. Like I said, this double ket notation is, instead of writing vec, I write a double ket. Okay? To see that this action is legit, notice that if I now do and I use this identity, this is GK, this is complex conjugate but not transpose. Okay? But now notice, remember, this isomorphism is between bounded operators on H and H tensor H. This is a basis for H. This is a basis for H as well, because if I do complex conjugation, it's still an isomorphism. So what I have here is a basis for this space. Okay, so if I take the sum over all this, I have an orthonormal basis, and I'm expressing A with respect to that basis. Okay, so let me just write it here. These coefficients here you get, because if you remember, this inner product now is equivalent to this inner product. Right? So these coefficients here you get by simply doing an expansion in this basis. Okay? And this is essentially the proof that you can always write it like this. This CKL are given like this. Okay? And now I also make an observation, a remark. We call that hermeticity preserving was this property. Then this matrix of coefficients is also Hermitian. Okay? Yes?
Sorry, just one sec. Go back. I'm a little bit confused about the formula for the CKL, because the A is just in B of H, right?
Mm-hmm.
So the G tensor G is acting on B of H tensor.
Yes. Sorry, I should have said. This is a basis for H tensor H. Where is it? Here, but remember, these are isomorphic under this vec. So this is also a basis for B, H tensor BH. Ah, sorry. No, it's correct. Because remember, this operator takes objects from H to H. Yeah. Right? So you want to transform it to something that also takes objects from H to H, which means that you do a pre-processing, then the operator, then a post-processing. This is why you look at it like this. Okay?
But I'm still a little confused about whether the G tensor G acts on the same space as the A as a member.
Yes, in vector form. So, okay, if I write it this way, you're right. Then maybe I should say like this. Okay? No, but then it's a complete orthonormal basis. For any A in BH, this is true. Yes, okay. It is in BH because you want something, this map, this map takes objects from BH to BH, right? So, one GK dagger is for one BH, the input, and the other one is for the output. So this thing is here. The point being that what you do with this vec here is you're essentially transforming this from this to this, you're transforming it to a tensor product, right? And then what I do is I have a basis for the input space and a basis for the output space, right? And then if I wrote it in vector form, it would look like this. And if I undo the vector, then it becomes this.
So in the expression for CKL at the bottom there,
yeah.
Should that be the vector of A?
It's equivalent, actually, no? Okay. Because this, I can write this if you want as like that, okay. Right? And then maybe like that, something like that, right? Yeah. Okay. This is a Hilbert-Schmidt product, so it's essentially like this trick here, right? This thing here. So you get, it's you doing, how can I put this? So you have a vector A, right? And normally, if you have a state psi, normally you do this decomposition, right? Joe? Right? Okay, this is the same thing. It's just that the bases now are these operators. Okay, so we're doing exactly the same thing here. Okay, so this CKL is this basis. Okay? In fact, yeah. If you want, I don't know if this is correct. I don't think you vectorize here. I think you just take like a trace or a projection onto A. I don't remember. But yeah, it's essentially this trick here. Okay, same thing. Okay. Okay, in fact, we're almost there. Now with this form, okay, we can now get the structure, the general structure of the generator, okay? So here's lemma 3. And here's the tricky part, is I'm going to define this last operator as the normalized identity. The rest are traceless, okay? So if this were, for example, a two-dimensional Hilbert space, this would be the normalized identity and the normalized Pauli matrices, okay? This would be a proper orthonormal basis, or at least one choice. Notice that this sum is excluding the identity. So this is already the Lindblad. You recognize it already as the Lindblad operator, okay? In all but shape. The only thing that's missing is essentially diagonalizing this matrix and these operators so that we can write it in this LK, LLK, okay? But in general, this is the Lindblad master equation, okay? The only thing I haven't assumed yet is, or the only thing, after we prove this, the only thing that we have to prove is that this matrix here is positive semi-definite to show that the rates are all positive, okay? Now, to prove this, we start from this expression here, okay? We're gonna plug things in and just rearrange, so it's just a bunch of algebra, okay? There's nothing sinister. Once you have this form, it's actually easy to prove. So let's go ahead and do it, because it's a little bit tricky. Algebra. So I hope to, oops. I might need two boards here, so let me delete this. Okay. So, here's the proof. right? This is what we proved in the previous lemma. Okay, first thing is I'm going to separate the terms that correspond to the operator we defined as the identity. So this is equal to Cn squared over root n. That will be identity, so this is just A. Okay? Then we have two terms, one in which I choose k to be n squared and L everything else, and one in which I choose L to be n squared and everything else. So they will look like this. Okay? So far so good? Right? Okay? Just a little bit of rearranging. I'm going to group these two terms together. Okay, since it's a dummy index, I can always write it like this. Okay? Yes? I just group them together. Okay? Why did I do that? Because if you notice, this guy looks eerily similar, like doing a very special thing in operators. Okay? So we have and since remember, L is hermeticity preserving, it follows that this is true. Okay? And with this definition, I can write this as Cn squared over n. Sorry. Agreed? I'm going to write this operator into its Hermitian and anti-Hermitian part, where this operator K Both of these operators are Hermitian. Okay? And then if I substitute and rearrange, I will get okay? I substitute inside the expression, and what I will get is the following. If you want, let me just write it like this. I'll just put the identity for a reason that will become clear in a bit. Oh no, sorry. Let's not, okay. It's A plus AK plus K dagger A minus I HA minus AH okay? Now what I'm going to do is the following thing. I'm going to break this first term into two parts. One of them I'm going to insert the identity on the left, and the other one I'm going to insert the identity on the right. The rest I'm going to keep the same. I'm going to already substitute this for this guy here. Okay? The reason why I did this is because now, right, I can define an operator where all the A's are on the left and another operator where all the A's are on the right. In particular, I'm going to call this operator F. This operator is given by C n squared over 2, the identity, plus K. I think there's an n missing. Yes. Okay? And if I do that, this is starting to take shape. We have HA plus, here I have the anti-commutator of this operator F with A, plus the sum KL equals 1 to n squared minus 1 CKL GKA GL dagger. Okay? Now it doesn't look at all like what we wanted, but now remember that the condition of the theorem was that the trace of this operator is 0. Okay? For any A, the trace of this operator has to be 0. Okay? The trace of the commutator is always 0, whatever the operators. So this is 0. This is 2 times the trace of FA. Yes? Actually, let me write it like this. The trace right? But now inside the trace, I can move things around, right? So this is equal to the trace of 2 times f plus the sum. If I move this operator over to this side so that a is always on the right, I get CKL, GL dagger, GK, this thing, multiplying a, right? But this has to be 0 for all a, which implies that 2f must be equal to, or rather f must be equal to minus 1/2 sum over KL, CKL, G, L dagger, GK. Okay? And if you substitute that inside this equation here and rewrite things around, you're going to end up with the final expression. Okay? That's the only other trick. So I'll skip that proof. It's just substituting things inside here and rearranging, and then you can get the final expression. Okay? Good. So we are almost there. Okay? One last thing. Now we have the general form. The only thing that we need to prove is that this is the generator of a completely positive dynamical semigroup. Okay? We have a small lemma before we do that, and then the proof is actually kind of simple. If you remember all these results, I'm just going to say by this, by this, by this, and then you see it, okay? So, one final lemma. Remember what is the idea? Is that we had a theorem that said that if you prove that if we have a dynamical semigroup on the extended space, right? If and only if the original thing was completely positive, right? So the only thing that we're left to do now is to prove that if I have the extension of, so if I have something which is a dynamical semigroup on the extension, where the dynamical thing is generated by this L, right? Then this is a CP thing. That's the only thing. And in order to prove that, the only thing we have to prove now is if L has this form, we have to prove that if it's dynamical, then it has to preserve the trace and it has to be positive, right? That's the only things left to show. So in order to do that, we need to define a set of orthonormal, a complete orthonormal basis on the extended space. And this lemma is doing exactly this, okay? It says let Actually, what we're going to define is a set of projectors. That's what we need, actually, right? So this is a complete family of mutually orthogonal projectors. Right? Because remember, in order for us to prove the dynamical part, we need to show that if I elect two elements from here and I take the trace, it's 0, and then if I take it's always positive. So first of all, we need to show that this guy is what I claim it is. Actually, it's not so hard to do, okay? And I am going to do the calculation because there's something very important and very neat that you need to see here, okay, regarding this extension, okay, which is very, very important. It's a property that we're going to use a lot, okay? And that's right, 10 more minutes and we're done, okay? So here's the proof. So it's a complete family of mutually orthogonal projectors. So I need to prove that if I multiply any two of these projectors, if they're different, I get 0. If they're the same, I get the projector back. And I need to also prove that they sum up to the identity, right? So the first thing is, let's take the dagger of this guy. Well, this is equal to the sum over KL1, 2n squared. This is G alpha KL, G alpha dagger, tensor KL. Sorry, this is a dagger. I have to take the dagger of this, which just flips these guys, LK, okay? And this is equal to sum over KL equals 1, 2n squared. This, remember, I have to flip the order and take daggers. So this is just G alpha, L, K, G alpha dagger, tensor, L, K. But all I did is just reverse dummy indices. So this is the same thing as PA. So for sure, they are projectors. Okay? The next thing we need to prove is that they are orthogonal. So if I multiply any two of them, what do I get? Multiply this guy. Right? I have G alpha, K, L, G alpha dagger, G beta, M, N, G beta dagger, tensor. Here I have K, L, M, N. Right? I have a delta here. Which means I will kill the sum over M. So I have K, L, and N. Everywhere I see M, I put L. Yeah? Now can everyone see it? Here, let me write it with a different letter. Yeah, let's use the black one. I have an L here. I have an L here. And I have an L here. What's this sum? Well, that's just the trace, right? So this is actually equal to the sum over Kn. This is just the trace of G alpha dagger, G beta, GAK N G beta dagger, tensor Kn. Remember, these guys are orthonormal, so I have a delta alpha beta, which means that I replace the betas by alphas, and I get back delta alpha beta by alpha. Right? And that they sum up to the identity is also a very, very simple proof. I'll just leave it for you guys to do, okay? The proof is that they're projectors. So finally, we get to what is known as the Gorini Kossakowski Sudarshan theorem, okay? Which is the last thing that I'm going to do for today. Which is, like I said, it's essentially us using what I wrote down as lemma 2, that if I prove now that this generator extended on this basis is, the trace of it is 0 and it's positive, then I prove that the extended dynamical map is positive. And by lemma 2, this can happen if and only if the original map, unextended one, is completely positive. Right? So that's the only thing we have to do. Okay? So, here I will write it down so that you guys can also have it. Is the generator of a completely positive dynamical semigroup if and only if Okay, this is the theorem. Now, the proof is very fast, so here, let's go, because we are essentially going to use all the results we have proven so far. Okay. So again, we have an if and only if part. So the first thing we're going to do is we're going to assume that this guy is the generator of a dynamical semigroup on the extended space.
The trace of H equals 0?
Yes. Yes. The reason is that you can always, this is the gauge. You can always choose a trace to be of h equal to 0 because any other shift you do is just a gauge transformation. Okay? So the first thing we're going to do is we're going to assume that this is true, and then we're going to show that this is the generator of a completely positive dynamical semigroup. Okay? So proof. Assume that L is as given. The way that I'm going to prove that it's a generator of a completely positive dynamical semigroup is that I'm going to prove that we need to show that sum over A, the trace pi A L tensor the identity on pi B. This is 0 for all beta. And 2, we need to show that the trace of pi A L tensor identity on pi beta right? The idea being that this will then be the generator of a dynamical semigroup on the extended space, and by theorem 2, this is if and only if the original thing is CP. Okay? So, in order to prove 1, right, we write the generators as we had them before. So we have the sum over A, the trace. Here we have to put this pi alpha generator, which if you remember was a sum from 1 to n squared, G alpha KL, G alpha dagger tensor KL, right? That was pi A, and then we need to have the L identity on this guy here, sum over Mn, G beta M n tensor Mn. Okay? Okay, if you do this, you're going to get 3 terms, okay? The first one is a term that's going to involve the Hamiltonian. You're going to get something like this. Let me see. Yep. And then we have the trace. You're going to get something like this, okay? G alpha KL G alpha dagger. And here you're going to get H G beta L K G beta dagger. This is important that the order switch. The reason is because remember the L with the M here, so it switches the order. And then you're going to get 2 more terms. One of them is this one, 1/2 sum over KL equals 1 to n, sum over ij 1 to n squared minus 1, Cij. And here you're going to get the trace of plus another term this first part is the same. But this switches. You have GI, G beta here with L, K, okay? All you have to do now is look at each term separately under this trace and play all these tricks of moving things around. You're going to notice always that there's going to be some cancellation which is going to involve traces, okay? So without going to the calculation, I can tell you that this term here is 0, okay? And these other two terms is exactly the same. These two terms are equal, okay? So I will get in the end, what you get is that they look like this. Okay? Wait, what did I do here? Did I skip something? Ah, sorry. This is for condition 2. Sorry. Condition 1 is trivial to see because if you use lemma 4, all the commutators, if you take the trace and so on, is 0. Okay? So for condition 2 now, you just have this thing. And you have to prove that this is bigger than or equal to 0. And the reason why this is important is because remember for condition 2, alpha is not equal to beta, which means that this term goes away, and you just have this term here. But this term is actually a positive number. Why? Because you can, if you look very closely, this is a complex number, and this is the conjugate of that complex number. Okay? If you cannot see this, notice that, so this here, this number here is the trace of G alpha dagger, G, I think this is a GI actually. No? Wait. I did something wrong here. One second, guys. Yes, no, it's okay. This is GJ. So remember, these are all going to be G alpha now because alpha is equal to beta. So this is the trace. This is this thing, okay? And to see that this is the same complex number multiplied by itself, this is multiplied by Cij. The assumption is that this matrix C is Hermitian and positive, which means that there exists a basis in which this sum here can be written as the sum over K, some lambda K, the trace of and now you see this is the same, is the complex conjugate. Sorry, I forgot to do this. Yep. This is alpha, sorry. That's because delta alpha beta, no? So the idea is that, remember, this was a Hermitian matrix which can be diagonalized, which means that there exists a basis of operators. In particular, this Lk can be written as the sum over, I don't know, n, u, k, n, gn, that diagonalizes this matrix. And now it's evident that this number here is positive, this is positive, so all of these guys are positive and bigger than 0. Okay? The converse is actually very easy, because now if we assume that L generates a completely positive dynamical semigroup, then L is hermiticity preserving, and the trace of L on any A is 0. Okay? And if we use lemma 3, L can be written in this form, in this general form here. Okay? And then since it's generating a completely positive thing, it must be that this matrix here is positive semi-definite. Okay? That's essentially the proof. Let me see. Right. Correct? Exactly. So as L is a completely positive generator, essentially what you do is you now write for the converse. Remember, if we do this change of basis, we can write this LA as minus I HA plus 1/2. Here we have a sum over K, lambda K, LK A LK dagger plus LKA LK dagger. Since by assumption this generates a completely positive dynamical semigroup, it means that if I do this tensor the identity, this must be a dynamical semigroup, which means that I have to show that the trace of ALA is 0 and it's positive, and the proof is exactly the same as here once you have these forms. Okay? This is what we have already proven, and that's it. Okay? So this proves this general form. Actually, I find it oftentimes much more useful to work with this form. The reason being that if this matrix is very big, it might be very difficult to diagonalize, but you can at least hardcore program this into your favorite mathematical software package, be it MATLAB or Mathematica or Python, in such a way so that I give you a matrix here, and then it computes directly the generator, and then you can do the exponential of the generator, and so on and so forth, okay? And that is essentially the proof of the Gorini, Kossakowski, Sudarshan. Any questions before we? Was it clear? I mean, what I've skipped is essentially just steps of the proof, and what I've skipped in this second part is really trivial, because if you assume that the generator is a CP dynamical thing, then essentially all you have to show is this properties here, and the calculation is the same as here. Okay, you just go ahead and do it. Okay. well, in addition to the assumption that since you assume it that it's a trace of 0 and positive, it has to have this form, and then you go and prove it, okay? Good, that is it. Next lecture, I don't know if it's gonna be next week or the week after. The next lecture will be, we're not gonna look at generators, we're just gonna look at dynamical maps and how to represent these maps, okay? So we're gonna look at specifically this Choi-Jamiolkowski representation, the Kraus representation, the Stinespring dilation, all these things, okay? Thanks, that's it.